prove by direct proof. So if a is an odd integer, then 2a plus 3a plus 5 is also odd. So we're going to assume that since a is odd, a is equal to 2k plus 1, where k is an element of the set of all integers. Therefore, we're going to take our equation 2a plus 3a plus 5 and set that also equal to 2k plus 1. And by solving that out, by subtracting 5 minus 1 and adding these two like terms together, we're given 5a is equal to 2k minus 4. We divide 5 by both sides, and we're left off with a is equal to 2k minus 4 divided by 5. And if we take this value of a and we plug it back into the original equation here, we're left off with 2 times 2k minus 4 all over 5 plus 3 times 2k minus 4 all over 5 plus 5. And if we evaluate this out here, we're left off with 4k minus 8 all divided by 5. Over here is 6k minus 12 all divided by 5 plus 5. And just to clean this up, we're going to multiply all of this by 5, and these 5s will cancel, leaving us with 4k minus 8 plus 6k minus 12 plus 25. And if we bring it over here, with 4k minus 8 plus 6k minus 12 plus 25, and by like terms, 4k and 6k together will give us 10k, minus 8 minus 12 together will give us minus 20, giving us 10k minus 20 plus 25. Further evaluating to 10k plus 5. And if we take all of this and divide it by 5, we're left off with 2k plus 1. Therefore, by direct proof, 2a plus 3a plus 5 is odd.
We'll be using principle of mathematical induction by proving that the summation of n equals n multiplied by the quantity n plus 1 all over 2. Our first step is proving the base case. By doing that, we'll be replacing your n with the value of 1. Your left side will be 1, which will then equal to 1 multiplied by the quantity 1 plus 1 all over 2, which your left side equals 1, and your right side will also equal 1, therefore holding true. Our second step is to do the inductive step, which in part A of the inductive step, it's assuming that statement is true when n equals k. So setting up the problem, you will be showing that 1 plus 2 plus 3 plus so forth plus k equals k multiplied by the quantity k plus 1 all over 2. And to show that the n equals k plus 1, and if that holds true, you can see how you have the 1 plus 2 plus 3 plus k also equals to what you just did in part A. So replacing that with the statement you already proved in part A, you will get k multiplied by the quantity k plus 1 over 2 plus k plus 1, which will then equal the right-hand side after you've replaced your n's with k plus 1 instead, will equal quantity k plus 1 multiplied by the quantity k plus 1 all over 2. To simplify and to make sure that both statements will equal each other, you will then end up getting quantity k plus 1 plus quantity k plus 2 over 2 for the left-hand side. And after simplifying the right-hand side, you will then get quantity k plus 1 plus quantity k plus 2 all over 2. Therefore, they are equal each other, and proven by PMI that the summation of n equals n multiplied by the quantity n plus 1 all over 2.
All right, so for this problem, we're going to be using direct proof in order to prove the problem. The problem states that x and y are elements of the set of integers. It also states that if x and y are odd, then the multiplication of x and y is also odd. To prove it, we are going to assume that both x and y are odd integers, meaning x equals 2a plus 1 and y equals 2b plus 1, where a and b are also any integer. Over here we have my problem solution, where it shows that x times y can be written as 2a plus 1 times 2b plus 1. We're going to go ahead and multiply both of those, and we're going to be left with 4ab plus 2a plus 2b equals plus 1. We're going to go ahead and factor out a 2, and we're going to be left with 2 times 2ab plus a plus b, and I went ahead and took out the 1 as well. By doing that, we can simplify to 2k plus 1, where k equals 2ab plus a plus b is also an element of the set of integers. And as you can see, 2k plus 1 is also the same to when we made x equals 2a plus 1 and y equals 2b plus 1, meaning, or therefore, the result of x times y is an odd integer proven by using direct proof. Quod erat demonstratum. I definitely said that wrong, but thank you very much.